this lecture, we will learn about optimization problems and the strategy to optimize the given problem. So we follow the following steps in order to optimize a given problem. In the first step, we read the problem carefully until we understand it, and we also identify the unknown quantities and the given quantities and the conditions. Then, using the given relationship among the variables, you construct the mathematical model. So you maximize or minimize the model here. The model is always the given function. And then, using the previously known methods from the other sections of chapter 4, we want to find the max or the min of the given function and the point x at which this max or min occurs. And then we use the solution to answer all the questions asked in the problem. So here are a few examples. Let's do the first one. Find the dimensions of a rectangle with area 1000 meters square whose perimeter is as small as possible. So area is given for you. Area is 1000 meters square and perimeter is as small as possible. So you're minimizing the perimeter. So area of the rectangle formula, you know that area of a rectangle equal to length times the width. So let me write the area is 1000. I'm going to write it as length times the width. But let me rename the length and width as variable x and y because we are more used to differentiating variables x and y. And I'm going to calculate y from this. It will be 1000 divided by x. So in the very first step, you will read the problem carefully. Note down the unknowns in the problem. Question is asking you the dimensions. Find the dimensions. So unknowns or the dimensions in the problem, the length and the width. And also the given quantities, which is the area. So this is given. And unknowns will be the length and the width. Or we renamed it as x and y. So x and y is the unknown, which are actually the length and the width of the rectangle. And you also noted that you want to minimize the perimeter function. So whatever is the function you maximize or minimize, you want to write that in the next step. So perimeter of the rectangle. The meaning of the perimeter is sum of all the sides. So you sum all the sides. The sides are x and y. So you have 2x plus 2y. Rename the perimeter in any problem as f of x. You wrote f of x on the left hand side. But on the right hand side you have x and y term. So it should be only x term. So replace this y in terms of x. So I'm going to write y as 1000 divided by x. Now I'm going to simplify this a little bit. I'm going to write this as 2x plus 2000 divided by x. After deriving, we'll be able to identify the minimum or the max value. So let me do the derivative of this function f prime. I do the power rule of differentiation. So let me rewrite this as 2x plus 2000 times x to the negative 1. So derivative of 2x is 2. Derivative of the exponential function x to the negative 1 will be 2000 divided by x to the negative 2. So it's x to the 2. Then you want to equate f prime to 0. So 2000, 2 minus 2000 divided by x square is 0. Solve for x and you see that x is 1000. You have a x square is 1000, so you have a plus or minus square root 1000. And I'm going to choose the positive square root because the sides cannot be negative. Now let me do the second derivative f double prime, which is negative 2000 times negative 2 times x to the negative 3. So this is 4000 times x to the negative 3, or it's 4000 divided by x to the negative 3. Now you want to evaluate f double prime at this particular value, which is x. We did find that x is root 1000, so we want to evaluate this at root 1000. When you plug in, you don't want the simplified answer, but rather you just want the sign of the function. The sign of the function will be positive, so you're going to write it as greater than 0. So f double prime greater than 0, you know that this is the concave up curve when the second derivative is greater than 0. So the function will have a minimum at this point. The function in the problem is the perimeter, so you did minimize the perimeter in the problem. Also, the question asks you to find the dimensions when you're minimizing the perimeter. So we did find x. Let's go back and plug in the y value 1000 divided by x, which is 1000 divided by root 1000. So your answer will be still the same, root 1000. In the next example, find the two positive numbers whose product is 100 and whose sum is minimum. Let the numbers be x and y, and you understand that these two numbers are positive numbers. That's our assumption. So the product of the number can be written as x times y equal to 100, and the sum is minimized. The sum of the number is x plus y, and you are trying to minimize this function. So first you write all the given quantities in the step 1. So you want to write step 1, the given quantities, x times y equal to 100. So do calculate the expression y value, which is 100 divided by x. Also, you are asked to find x and y, the two positive numbers. That's your question here. When you do find the x and y, you make sure that the sum is minimized. The sum in the problem is x plus y. This term is minimized. So whatever you're minimizing or maximizing, that will be the function for the problem. So let me write that in the second step. The function f of x, which you want to minimize in the problem, is the sum. You're minimizing the sum. So rewrite f of x is x plus y. On the left hand side you wrote it's a function of x, but on the right hand side you're writing a function of x and y. So this y should be rewritten in the form of x. So I'm going to plug in y as 100 divided by x. I'm going to rewrite this as x plus 100, x to the negative 1. Now I will be differentiating this in our step 3. So we know the model. So let us differentiate in our step 3 f prime. Differentiation of x is 1. Differentiation of x to the negative term will be negative 100 divided by x square. Equate f prime x equal to 0. Solve for x. You get x equal to 10. Now take this x equal to 10 and do derivative of f double prime. In the step 4, do f double prime, which is 200 divided by x cube. In the step 5, check the sign of this f double prime. Plug in x equal to 10. You have 200 divided by 10 cube. We are not worried about a simplified answer, but we are still worried about the sign of the term. It's positive. So when you have the second derivative to be positive, the curve is concave up, and you will have a minimum of the function here, and the function is the sum, so you can say that the sum is minimized. You also want to find the dimensions. We did find x, which is 10, so we also have y equal to 100 divided by x, so it's 100 divided by 10, which is 10. In the next example, the top and the bottom margins of the poster are 6 cm and the side margins are 4 cm. If the area of the printed material of the poster is 384 cm square, find the dimensions of the poster with the smallest area. So you want to first draw a poster and mark all these dimensions on this. So you have a printed area as well as the entire poster. So there are two sets of dimensions. So you have the poster's margin, the top and the bottom will be 6, so I'm going to write this as 6. And the side margins are 4, so I'm going to write this as 4. And you're also given that the area of the printed material, the print will be just the material which is typed, so it will be the inside ones, which is 384 meter square. And I'm going to name this dimensions length x and length y, so it's x times y equal to 384. Now let's move on to the entire poster. So the poster entire length will be x plus 8 because you're adding x plus 4 plus 4. And the width will be y plus 6, so it's y plus 12. So you're going to write x is the length of the printed part and y will be the width of the printed part. In the next line you will write area is area of the printed part equal to 384. So you will write x times y equal to 384. You will also calculate the y expression value, which is 384 divided by x value. Then you will write area of the poster. This is the entire poster. This is x plus 8 times y plus 12. When you simplify, you have xy plus 12x plus 8y plus 96. You multiply them out. And this area of the poster, the question is asking you find the dimensions of the poster with the smallest area. So this is the function for the problem, and you are minimizing this area. So in the step 1, you might want to note you have 3 steps, write all the given quantities unknown. Step 2 will be the model. Step 3, you're going to do some derivatives. Do f prime of the function. You have x times y is given for you. You can rewrite this as 384. So I'm going to write this as 384. When you derive, you will have the answer as 0. So don't write the 384. 12x, derive 12x, you have 12. Derive 8y. Y can be rewritten as 384 divided by x. Multiply 8 times 384 and then derive. Then you have negative sign and 3072 divided by x squared. Derive 96. It's 0. It's a constant, so don't write. Equate this to 0. Solve for x. You get x equal to 16. Then once you find f prime, you're good to find f double prime. Derive again. So you have negative 3072 times negative 2 times x to the negative 3. So this is 6144 divided by x cube. Evaluate this at 16. So you have 6144 divided by 16 cube, which again we are not worried about the simplified answer but the sign. So it's positive. Positive means f double prime positive concave up. You have a minimum of the function here. The function f is the entire area of the poster. So we did calculate the length of the poster. So we want to know the width of the poster. So let's do that. One last step, calculation of width of the poster. Width of the poster will be y equal to 384 divided by 16, which is 24. Again, x and y are not the width. You want to recalculate it by adding the side margins. So you want to write the length of the poster is 16 plus 8, which is 24, and the width of the poster will be 24 plus 12, which is 36. In the next example, A farmer plans to enclose a rectangular pasture adjacent to the river, and the pasture contains 45,000 square feet in order to provide enough grass for the herds. What dimensions will require the least amount of fencing if no fencing is needed along the river? When it comes to amount of fencing, you have to understand that it's the perimeter. And you see a word least amount, which means you're minimizing the perimeter. So let's write area in the problem equals x times y, and the area is given for us, which is 45,000 x times y. So you will be able to calculate an expression of y from this, which is 45,000 divided by x. Now in the next step, you want to write the perimeter of this pasture, which is y plus y. So you can write 2y, and then you are adding 1x. So the perimeter will be 2y plus x. So let's write the function, which is the model in the problem, is the perimeter, and rewrite this as x plus 2 times, rewrite y as 45,000 divided by x. So multiply this out, it's 90,000 divided by x. Now in the step 3, you want to calculate the f prime, the first derivative, and you have 1 minus 90,000 divided by x squared. Equate this to 0, solve for x, and you see that you get x equal to 300. In the step 4, I want you to find the f double prime, which is 180,000 divided by x cube. Evaluate this at 300, and you see it's positive. So y equals, as soon as you see it's positive, you know it's the curve is concave up, and at this point you have a minimum value. And the function here is the perimeter, so you are minimizing the perimeter. So y is 45,000 divided by x, which is 45,000 divided by 300, so it is 150. So you know the dimensions as well as you did minimize the perimeter. So in the next example, a circular cylindrical metal container open at the top is to have a capacity of 192 pi inch cube, and the cost of the material used for the bottom of the container is 15 cents per inch square, and that of the material used for the sides is 5 inches per inch square. 5 cents per inch square. If there is no waste of the material, find the dimensions that will minimize the cost of the material. So let's draw a cylindrical metal container. The container is open at the top, and the capacity will be 192, which means the volume is 192 pi inch cube. The radius is r and the height is h. The cost of the material used for the bottom of the container is 15 cents, and the material used for the sides is 5 cents. So first you want to write the volume expression, which is 192 pi. The formula for circular cylinder, the volume formula will be pi r square h. So equate that with 192 pi. You will be able to cancel these pi's, and all you have is r square h equal to 192. So you can say h is 192 divided by r square. So you have derived a formula for h. So this is your step 1. Also, you want to note carefully what are you trying to minimize in the problem. You are trying to minimize the cost function. So once you identify what is the variable you're minimizing, you want to write that in your step 2 as the first function to start with, cost function. And this is your model in the problem. And you want to bring down a formula for this cost function. So you have 15 cents as the price for the cost of material of the bottom of the container. The bottom of the container, the base area will be pi r square. So write it as pi r square. This is the base. And now you want to calculate the cost for the sides of the material. The cost is 5 cents times the side of the material. The area will be 2 pi RH. This is the side of the material of the circular cylinder. You might want to consider this as a flat sheet. If you open up the circular cylinder as a flat sheet, you understand that this area will be circular, so you're going to write it as 2 pi r, and you also have the height, which is h. So the cost in cents will be all this. So you want to multiply out and write this as 15 pi r square plus 10 pi rh. Now the first term is the same, whereas you can plug in for the second term and rewrite it as 10 pi r times 192 divided by r square. We're going to plug in for the h expression, the height, which we calculated in our step 1. Rewrite this again as 15 pi r square. Multiply this out, 1920 pi r to the negative 1. Now that we have a nice neat expression for r, in your step 3, you're good to differentiate c. Most likely, because most of the problems we have differentiated with respect to x, you may be tempted to differentiate with respect to x, but read the right hand side carefully. It is a function of r, function of r. If the right hand side is a function of r, your cost function c here on the left hand side is a function of r. It cannot be a function of x. So when you differentiate, it is a function of r and you are differentiating with respect to r. So differentiate 15r square, it is 30 pi r. Differentiate r to the negative 1 term, you have negative 1920 pi r to the negative 2. Now you want to find the critical points by solving c prime r equal to 0. So solve for r, simplify and check the r value. You get r cube equal to 64 after simplifying. So you can say r is 4. Now having found r value, you can plug in the expression for h, which is 192 divided by r square. Simplify, you get 12. But still we are not done with the problem because you have not identified whether you have minimized or maximized the function. So here is the step 4, which will justify whether you minimize or maximize. So calculate c double prime r, differentiate the c prime r again. You have 30 pi positive 3840 pi r to the negative 3. So you have 30 pi plus 3840 divided by r cube. Now we know that r is the radius which is greater than 0. We calculated it as 4. So for r greater than 0, if you plug in the r value in the c double prime expression here, you see that this c double prime will also be positive. We are not worried about the value but just about the sign. Finally, you get an expression which is positive. So as soon as you see c double prime, if the second derivative is greater than 0, the cost function is minimized here. You will have a concave up curve and it's minimized. So you're minimizing the cost. This is your step 5. And the question asks us to find the dimensions that will minimize the cost of the material. So the radius should be 4 inches and the height should be 12 inches, and this will minimize the cost of the material. We're going to end this section here.